Today's lecture is going to be on the Earth's moon. We're going to look at the formation and the evolution, kind of the theories as to leading to them. So there's a lot of evidence for the moon's violent past, and observations of the moon show that it's had a violent past. Technology and scientific testing also help prove that the moon's best supported storyline is not some of the early ones that have come out. Although it does have a chaotic history, the theories that try to explain the origins of the moon are the following. Fission theory, that it formed as a blob that was spun out from the rotating Earth. Now I've got a video that helped re-illustrate these, but we'll get into them. So fission theory, that it actually came from the Earth itself as the Earth was spinning, let's just say, fast, and it kind of blobbed itself out. Then there's capture theory, that the Earth captured it gravitationally, that maybe it was a passing planetesimal or object that the Earth's gravity was able to capture and hold on to. And condensation theory, that it formed at the same time as the Earth in the primitive accretion disk that formed the planets. Sometimes this is called accretion theory. But the giant impactor theory, this is the one and the only one theory that leads astrogeophysicists, or physics, storylines. A Mars-sized planet collided with the Earth about 4.5 billion years ago. And the ejecta, right, the material that blasted back out into space, then coalesced, right, it built upon itself into the moon. And this is best supported by the chemical makeup, its composition of the moon itself. Now, let's go back and take a look at geologic time for a second. That most of the lunar surface, right, we can see has these craters on it. Now, I encourage you to watch this video. But the bombardment that took place during the Precambrian eon, over 4 billion years ago. And this was called the Hadean, right, on Earth. In the Earth phase, we call this Hadean, hell on Earth. But since the moon lacks water, and the water cycle, erosion does not erase the lunar features. So they're pretty much there to stay. So if we look at a picture of the moon, the lunar surface, the physical and chemical evidence for the impactor theory are the following. It's got a bombarded surface, so let's not ignore the fact that observation is important here. Its composition is identical to the Earth's mantle, which would be consistent with the collision of it blasting out debris, not from the interior Earth, but from the outside or the external layers of the Earth. Earth's crust and mantle. Remember, the Earth's crust is tiny compared to the mantle. It lacks water, and it has a very, very low density. It's very low in iron. Now, when I say low density, we're talking the density is compositionally equivalent to that of about the Earth's mantle. So we could say that the Earth's mantle is compositionally, and some other features, the density of it, are consistent with the moon's features. So we have some evidences that are building an emergent storyline. So we're going to switch gears here. We're going to look at the moon's elliptical orbit. The Earth's orbit around the sun is elliptical. So too is the moon's orbit around the Earth. Earth's closest distance to the sun in its orbit is called perihelion. We've looked at this here, closest distance. And the Earth's furthest distance from the sun is called aphelion. So here's a picture of the Earth orbiting the sun, and it's exaggerated. It's just kind of illustrating our orbit isn't nearly this elliptical. But the closest and furthest distances of the Earth-Moon have names corresponding to the location of the two celestial bodies. And these terms are what we call perigee, where we say that the Moon's closest distance from the Earth, and apogee. So we can see it here as well. So this picture kind of puts them both together. And this kind of just isolates the Earth-Moon distances. So we call apogee, the greatest distance, right, A, away. It's about 250,000 miles away during apogee. And perigee is the moon's closest distance, is what we call this distance right here, closest distance from the moon, Earth. Syzygy, kind of a funky word, lots of Y's. This is the alignment of the Earth, Moon, Sun. The term syzygy occurs when the Earth, Moon, and Sun align. This occurs at two locations in the moon's orbit of Earth. When the moon is away from the sun, and what we call opposition over here. So here's the sun, here's the Earth, here's the moon. And the moon is on the far side. And when the moon is between the Earth, Sun, we call this conjunction. Conjunction. The moon is located between the Earth and the sun. And these occur at very specific lunar phases. Now, even though we haven't looked at lunar phases yet, we will. We'll talk about these a little bit further. Then we'll be talking about the new moon phase, where we actually cannot see the moon because the illuminated side is actually facing the sun. So we see the dark side, or the side that is not illuminated, so we don't see it. And then here we have our first quarter phase, our full moon phase, our third quarter phase, and then back to new moon. So we're going to be referencing the lunar phases very, very shortly. So what is taking place? How does the Earth, Moon, Sun system behave? Well, it's all a function of universal law of gravitation. And this is kind of our Newtonian explanation here, that we can say that the force of gravity is equal to this very, very tiny constant value times mass 1, mass 2, divided by the distance or the radius of the two objects squared. So the gravitational differential of the Earth-Moon system is responsible for tidal bulges in the ocean surface that is directly under the moon. Water is literally squeezed from the poles and moves outward due to being nearly incompressible. The Earth and Moon revolve around a common center of mass. We'll talk about this here very soon. It's called the barycenter. Because Earth is much more massive than the Moon, the center of the mass of the system, right, the Earth-Moon system, is within about 4,700 kilometers or 2,900 miles of Earth's center, which is about 1,000 miles below the Earth's surface. In other words, the center of mass of the Earth-Moon system is within the Earth. It's about 1,000 miles beneath the Earth's surface. This has been likened to like a seesaw with an adult seated at one end and a child at the other end. The pivot point, or the center between the system, must be moved towards the adult for the two individuals to balance the seesaw. In other words, we can treat the Earth like the adult and the Moon like the child, that the center mass is going to be closer to the larger object, in this case the Earth. So the Earth-Moon system. The barycenter of the Earth-Moon system is located about 1,000 miles beneath the Earth's surface. This is the center of the average position of both objects, and we can see it here. So here's the Earth, here's the Moon, and the barycenter is within the Earth itself. The barycenter is not the very center of the Earth due to the average position of mass between the two objects. The Sun, so I'm hoping by now you're like, well, what the heck is the barycenter? Well, the Sun doesn't view the Earth or Moon as individual objects. Instead, the Sun's gravitational field acts upon the Earth-Moon center of mass, the barycenter. So the Earth's orbit is really more closely linked to the center of mass of the Earth-Moon system. And we can see in this picture here. So where the Moon is, and the Earth, where the average position, once again about 1,000 miles beneath the Earth's surface, we find the center of mass, and it's moving. So we would actually find that the barycenter here is moving as the Moon is orbiting the Earth itself. So the barycenter is located inside the Earth. It's about 1,000 miles, and it is constantly in motion, consistent with where the Earth-Moon position is located. So I want you to watch this video here. This helps explain the tides, and it really goes over some misconceptions. And you can watch, I want you to watch the whole thing, but I want you to go back and look at it from the 4-minute, 25-second to the 6-minute mark. It best illustrates how and why tides occur. It's contrary to much of the poor science that explains tides. But here's kind of a summary of it. The tides are the result of a gravitational difference, or differential, of the Moon acting on the Earth. Tides are not the result of water being stretched toward the Moon. And this is the common misconception. Instead, tidal bulges are the result of the net gravitational effect, pushing water by squeezing it inward. Water is nearly incompressible, so it bulges as a result. And in the video, it's going to show you that the net squeezing effect is going to have this effect on water gets kind of squeezed outward at the Moon-Earth line. If I were to draw a line here, so satellite, that would be the Moon. But the misleading example is that the tidal bulge is due to the attraction of the Moon. That's not true. It's the net effect of what we see taking place with these acceleration vectors. So watch the video. It'll help make sense of it. And then here's a short little video showing you what the tidal bulges actually look like. Kind of a nice little animation. And the last thing I have for you, it's kind of a switching gears one more time. It involves light. Photons move at c, the speed of light, 186,282 miles per second. We've talked about that countless times. So if we look at a photon leaving the sun and reaching the Earth, we can solve the time it takes, and we can use a very simple equation. Speed equals distance divided by time. That the speed of light equals distance divided by time, and therefore time we could solve is going to equal the distance divided by the speed. So a photon travels from the Earth to the Moon here. Well, we can look at the first one. We can say, well, the sun emits photons, right? Light from matter, E equals mc squared. And it takes about 500 seconds to travel to the Earth. we see photons that left the sun about 8.3 minutes ago. But photons reflect and are absorbed from the moon's surface. Remember, we studied the concept of albedo, that the lunar surface is not emitting light, instead it's reflecting sunlight. Then this light then travels through space to Earth, where we can see the reflected light. Remember, we see most of our world by reflected light. The distances can be calculated by using the speed of light, 186,282 miles per second, and the average distance to the moon, about 258,000 miles. So when we look at how long it takes here, make sure you note that this should be 238,900 miles. That was a 5 there. That was definitely incorrect. So about 239,000 miles. So you can calculate how much time does it take the photon to travel this distance, traveling at this speed. So the average Earth-Moon distance is about 239,000 miles, and the average Earth-Sun distance is about 93 million miles. So we can do some very simple math to calculate how long it takes from the photon to travel from the sun to the Earth, and for the photon to reflect off of the moon and reach our eyes on Earth, about 239,000 miles away. There you go.